Hello, everyone. In this lecture, we will learn some behaviors of graphs of functions. And well, let's start with the symmetry of the graph of a function. Now we say the graph of a function is symmetric with respect to the y-axis. If well, first let's consider an equation of two variables x and y. Suppose we have an equation of the variables x and y. Now, we know how to plot the graph, right? And we say the graph of this equation of x and y, is symmetric with respect to the y-axis if we substitute, let me write it here, if negative x for x equation. Okay, so in that equation, in whatever that equation of x and y is, if we substitute negative x for x, and if we get the same equation, well, that's when we say the graph is symmetric with respect to the y-axis. Okay, and then consider again the same equation of x and y, and then this equation, or the graph of this equation, is symmetric with respect to x-axis if when we substitute negative y for y, if it results the same equation. Okay, if the result is the same equation, then we say the graph is symmetric with respect to the x-axis. And again, we have the third symmetry, which is with respect to the origin. And here in this case, we combine these two. If substituting negative x for x and negative y for y at the same time, if the result is the same equation, then we say it's symmetric with respect to the origin. Now, for example, a simple example, let's consider here y equals to x squared. Right, this is a parabola. This is, y equals to x squared. Now, if you substitute negative x for x, then we get y equals to negative x squared, which is still x squared. Okay, so we started with this one, and we end up with the same equation. Therefore, as you can see, when we substitute negative x for x, we get the same or equivalent equation. Therefore, the graph of this function is symmetric with respect to y-axis. Okay, but if I substitute negative y for y, I will just get this one, which is not the same with this one. Okay, therefore, we know it's not symmetric with respect to x-axis, and similarly, it's not symmetric with respect to the origin. And again, if you take, for example, the simple example, y equals to x, definitely it's not symmetric with respect to y-axis, because if you substitute negative x for x, you don't get the same result. It's not symmetric with respect to y-axis, x-axis, again, with the same idea, same reasoning. But how about the last one? Well, let's try it. Substitute negative y for y and negative x for x. Therefore, we have negative y equals to negative x. And if we multiply both sides by negative 1, okay, then we get y equals to x, which is the same. Therefore, the graph of this equation is symmetric with respect to the origin. Now, another behavior is determining whether a function is an even function or an odd function. Now, first, what do we mean by even and odd? We know the terms even and odd in real numbers, right? So for functions, we call a function is an even function if f of negative x, which means if we substitute negative x for x, and if we get the original function f of x for all x in the domain, okay, then we say this function f of x, this f of x, the x function is, or this f function is an even function. Okay, so an even function, any even function, is symmetric with respect to the y-axis, because this is the same concept with what we have over here. Substituting negative x for x, if it results with the same or equivalent equation, then we say this is symmetric with respect to y-axis, and this is similar idea. So even function, the definition is for every x in the domain, if f of negative x is f of x, then that's an even function. And from the above, from the symmetric properties, this is the behavior of the functions which are symmetric with respect to the y-axis. Therefore, every even function is symmetric with respect to the y-axis. And an odd function is when we substitute negative x, if the output is negative of f of x, then we call this one odd function. Okay, this is an even function. Right? So if we have an odd function, any odd function is symmetric with respect to the origin. Okay, therefore, an even and odd functions, one of them is symmetric with respect to the y-axis, and the other is with respect to the origin, not with the x-axis. Now let's consider this graphs and try to determine if they are symmetric with respect to, if they are even or odd. Okay. Now, if we look at this one, just by looking at this, this is symmetric with respect to the vertical line, which is the y-axis. Okay. With respect, I'll write it in short. With respect to the y-axis. Okay. So with respect to the y-axis, therefore, here we have the function f of x. Therefore, f of x, or just f, is an even function. Okay. So I can determine whether the function whose graph is this one is an even function or odd function just by looking at the graph, because we look at the symmetry. Is this symmetric with respect to the y-axis or the origin? Okay. Or sometimes it's not always. Sometimes it could be even neither, right? So it doesn't have to always be symmetric with respect to the y-axis or the origin. And again, if we go to part B, now here we have, well, separate lines. It's not only one line. We have some discontinuity. Therefore, if I look at this, for example, we have this, and if you reflect this one to the, with respect to the origin, then you will get this. And definitely, this line is symmetric with respect to the origin. Okay. Again, if I reflect this one to the other side, assuming, let's say, this origin is our mirror now, then we get this image. Okay. So this is an image of this one. And this part is an image of this part, or this part is an image of this part. Therefore, f here is not f. The graph is symmetric with respect to the origin. Therefore, f has to be odd function. Okay, since it's symmetric with respect to the origin, it's an odd function. The third one, well, it's not symmetric with respect to the y-axis or with respect to the origin. Therefore, this function f is neither even nor odd function. Okay, because there is no symmetry in here in the graph. Now, how about if, well, we saw when we have the graph, we can determine whether the function is an even function or an odd function or neither. But how about if we have the function, the equation, or the function itself? Now, let's consider this example now. I have -4x to the power 5 plus 2x cubed plus x. Now, let's evaluate this one because the definition, or to differentiate between even function or an odd function, we just need to test what is f of -x. Try to look at this function, evaluate this function, or the function f at -x, and then look at the result. So let's see. F of -x, now replace on this side for every value of x, or every x, replace it by -x. Therefore, I will have -4, -x to the power of 5, plus 2 -x to the power of 3, plus -x. What do we have here? Here I have -4. Well, this is -x to the power of 4, right? Because -x to the power of 5 is -x to the power of 4 times -x, right? This is positive. And -x, you can take out the negative, so I have x. Therefore, this is just -x to the power of 5. Therefore, we have negative times negative. This becomes positive. And I will just ignore that one. I will write 4x to the power of 5 plus, again, with similar idea, because when you look at the power, right, at the exponent, if there's an odd value, and then the negative will still be negative. Okay, if this is negative, then the output will be still negative. Therefore, this is -2x cubed minus x. Now we need to still tweak a bit so that we can see whether this is f of x or negative f of x. Okay. Well, definitely this is not f of x, because f of x is this one, the original function. So they are not the same. At least we can see there is no negative here, right? And here it's positive but negative, negative, positive, right? How about if I take out, if I factor out -1? What do we get? We get -4x to the power of 5. This becomes positive, and this becomes positive. And exactly this is what our f of x is. Therefore, this is negative f of x. Okay, so what do we say? Since f of -x, f of -x is negative f of x, the function f is an odd function. Okay, and Well, since it's an odd function, we know it's an odd function. It cannot be an even function, right? So it's either an even or odd function, or neither of them. And then this one, f of negative x is negative x cubed over 2 times negative x minus 1 cubed. This is negative x cubed over 2 times negative, well, I can factor this out. So I will have negative 2x plus 1 cubed. So this is totally different from f of x. It's different from negative f of x. Okay, it's neither of them. There is no way we can convert this one to this or to this one. Therefore, f is odd nor even. Okay. All right. And next is we will now introduce a new type of function, which is called the piecewise function. In this case, we define the function in different rules. Normally, what we know is f of x equals, for example, 2x plus 1. This is the rule for the function, right? The relationship between x and the y value. So we have one rule for all domains of the function. In this case, the function g of x, it has different values or functions. Well, not functions, but it do have different rules for different parts of the intervals of the domain. As you can see, these are the domain, but we separate or we split the domain into 3 parts. One interval is all values. If this is -2, so we have -2 is included. So I will put this. And then we have close parenthesis up to 3. Again, sorry, open parenthesis. And then we have greater than 3 all the way to the right. So we have these 3 parts, these 3 intervals. This is the domain of the function g. So basically, the domain is all real numbers because the first one is going all the way to the left, and then we have in between, and then we have all the way to the right. So if we combine all together, we have the whole real number line. But the thing is, for each interval, for this each of these 3 intervals, we have different definitions. Here, f of g of x is -2 absolute value of x minus 3. Here, in this interval, g of x is 5x plus 6. And here, g of x is just 4. Okay, so these are what we are saying, what we call different rules. And that's why we call it a piecewise function, because we have one piece here, another piece, another piece. It could be more than 3 rules, or maybe just 2 rules. Okay. So how do we graph a function, or how can we evaluate a function? First, let's see if we can evaluate, or so let's see how we evaluate this. Now, to find, let's say, for example, g of -3. Now, this is value of x. Well, we are asked to evaluate this function at x equals to -3. Now, where is x equals to -3? Where does this value falls? Is it on this interval, or the last interval? As you can see, this is with the first interval, because -3 is less than -2. Therefore, this domain or this value of x is in this domain or in this interval. And in this interval, the definition of g of x is this one. Therefore, we take the first value, the first definition or the first rule. So g of -3 is -2 absolute value of x is negative 3 minus 3. Negative 2, absolute value of negative 3 is positive 3 minus 3. This is negative 6 minus 3, and we have negative 9. Okay, so this is how we evaluate. And how about g of let's say 0? Again, 0 falls in this interval, the second interval. Therefore, I take the second value. So g of 0 is negative 2, 0, negative 3. So this is just basically 0. This is negative 3. And similarly, we can find, we can evaluate, for example, g of 10. And 10 again is in this interval. Okay, in this interval. Therefore, we take this root, and that's just 4 because this is a constant function. Now the question is, how can we graph or how can we plot the function or the graph of the function? Okay, so if we take this, now we have, this is 3, negative, here we have negative 2, because I'm trying to find the borders. This is 1 and this is the other one. Okay, and for the first one, for x plus or equal to negative 2, the function is negative 2x absolute value of x minus 3. So we have g of x equals negative 2 absolute value of x minus 3. And this is when x is below negative 2. Now let's plot this graph. Okay, basically, what is this function without this restriction, for example? How does it look like? Without the restriction, I mean this less than or equal to negative 2. So this is, we know how to transform functions, right? The graph of function now. So if we take this as a parent function, it will be upside down. It opens upwards like this one. But now here we have negative, so it opens downwards. And then we have the 2. When we multiply it by 2, it shrinks here. So it becomes something like this. And then we subtract negative 2. This is a vertical shift. But since it's a negative, it's down here. Therefore, it starts from here. So basically, it starts from here if there was no restriction. Okay, but now there is a restriction. So this part that we had on here, if you continue from here, this is, let's say, the, so we have something like this. Okay, so the remaining part, we don't need it because it's not true. It's only, we have this function only on this interval. Okay, and the second function, g of x equals to 5x plus 6. Again, this we can use the transformation, or we can use the table of values. And here we have 1, 2, 3, 4, 5, 6 or something somewhere in here. And the slope is 5. So it's going to be something like, it's negative 2. What do we have? It's negative 4. So here we have something like this. And what's the x-intercept? It's gonna be -6/5. So somewhere in here, and the graph will be something like this. Okay. Well, not. I don't need this because it's only up to a certain point. So it goes up to this line, and then for x values greater or equal to 3, the function is defined by g of x equals to 4. And 4 is, for example, if it is here, so starting here, we have a straight line like this one. Okay, so this we put arrow, and on this one we put arrow. Okay, so this is how we draw or how we plot a graph of a piecewise function. All right, the next is determining or finding the intervals at which the function is increasing or decreasing or constant. So this is another behavior of the graph of a function. Now, when do we say a function is increasing in an interval? Now consider the interval I. So I is just an interval in the domain of the function f. So in I, in this interval, if to say f is an increasing function, we need to have f of x1 less than f of x2 for all x1 less than x2. Okay, so when x1 is less than x2, if this implies f of x1 is less than f of x2, then the function is increasing. And then on that interval, if when x1 is less than x2, if we have f of x1 greater than f of x2 for all values of x in that interval, then we have a decreasing function or decreasing. This is increasing. And if for all x1, f of x1 is f of x2, then we have constant. Okay. Now, looking at this graph, just the way, by just looking at this, as you can see, starting from here up to here, the graph is increasing, right? The line. So always we start with the left-hand side. When we go to the right side, if it is increasing, if it's going upward, then we say it's increasing. If it's horizontal, we say it's constant. And if it's going downward, we say it's decreasing. So now, in which intervals is this function increasing? The first one is here we have a point where x is -5 and y is -3. Okay, so we just need the domain or the x interval or the x values. So x value is between -5 to -3. -5 is inclusive, so between -5 and -3, it is increasing. There is another one here from -1 to +2. Union, this is addition, or we are combining the two of them together, -1, (2). And then decreasing. It's decreasing on this interval only, right? So that interval is from 2. Well, I'm just looking at x value. So this point is, at this point, x is 2, and then it's going all the way to infinity. So I just put this one. So the function is decreasing at this interval, and it's increasing at this interval and this interval, both of them. How about constant? Well, as you can see, it's constant at this because the graph is horizontal at this interval. Therefore, we have -3, -1. The graph is constant. Okay. All right. And the last one is determining relative minima and maxima of a function. Now, here, relative minima and relative maximum is, these are the plural terms of minimum and maximum. Minima is the plural of minimum, and maxima is the plural of maximum. Because we can have a lot of or many minimum values, so we use the plural value, the plural term. Now, this relative minima or maxima, sometimes we use local minima or local maxima. But here in this book, since our books use this term, I will still stick with this relative. Okay. Now, f of a, remember f of a is the value of y, not the value of x. Value of x is a itself. So f of a is relative maximum of f if there exists an open interval containing a such that f of a is greater or equal to f of x. So basically, when you look at the graph of the function, if the maximum value at this local if you take some interval, open interval like this one, and from all this line or this area or this interval, if this value is the highest or the maximum compared to around it, then we call this is local maximum or relative maximum. Okay, or if it is like this one, then we have a local minimum here. Okay, and f of b is relative minimum if there exists an open interval containing b such that f of b is less or equal to f of x. The reason why we need open interval is just using this one, okay, in which the endpoints are not included. If it is like this, if the endpoints are included, then we call it closed interval. So we need open interval here, not closed interval. So if we can find some open interval such that f of b is less or equal to f of x for all x in that interval, in this open interval, then we say the value f of b is local minimum. Okay. Now, if we look at this graph, going downward, it's not turning up, it's going down. Therefore, we don't expect to find local minimum or local maximum because it's going forever. Okay. And we know there is no end for this one, right? So if there is no end, then we cannot say there is minimum or maximum. Even though it may look here, this is the minimum value, but that's not the case because it's going. It's not stopping there. Now, but if I come here, and if I draw here an open interval here, if we put an open interval here, there is a point here, and this point is the highest point from the points around it, right? And this point is at x equals to -3. This is location of a local maximum, sorry, maximum. Okay, and the value of this local maximum is f of -3, which is 5. So this is the local maximum, or let me use relative. Okay, and then similarly, we have a point here, which is a relative minimum at x equals to 0. F of 0 equals to 0, because the y value again is 0, is relative minimum. Okay, and then here we have another local maximum, and that's at x equals to 3. So f of 3 is 5 again, is relative maximum. So as you can see from here, we can have many local maximum or relative maximum, or many relative minimum values. Okay, or sometimes we may not have local minimum or local maximum. For example, if you have the graph like this, then there is no way we can find local maximum or local minimum, because if you take an interval, if you take this point is higher than the points below it, but it's lower than these points. So there is no way we can find any point which is greater than all the other points. Okay, again, if you take somewhere in here, it's the same idea. And even if you have a graph like this one, again, there is no local maximum or local minimum. Okay, or even horizontal line like this one, because all the values are equal. Okay, therefore we have cases that we don't find local minimum or local maximum. Okay, all right, so this is all for this lecture, and see you in the next lecture.